So, section 3.4, part 2. All right, so just as a reminder, our properties that we're going to use, that we use for exponential equations, and we'll use them for logarithmic equations, are one-to-one properties for our functions. So a to the x equals a to the y, and log base a to the x equals log base a of y. Both of these are true if and only if x equals y. Those are one-to-one properties. The one that we'll use mainly for the logarithmic equations is the one that involves logarithms. So that's going to be one of the ones that we use today. And then our other property that we use for logarithmic equations are the inverse properties. And we use both of these a little bit, but the inverse property says that the log base a of a to the x equals x, and a to the log base a of x equals x. Those are the ones where we say the inverse functions undo each other, basically. And we'll use both of those today. So, using the same properties, our guidelines for solving these equations, similar to what we talked about for exponential equations. One way that we can solve them is to get the logarithm by itself on one side. And then we use the one-to-one property. Sorry, not the one-to-one property. Get the logarithm by itself, and then rewrite in exponential form, or use the inverse property. So that's one way we can solve logarithmic equations. Get the logarithm by itself, and then rewrite in exponential form. The other way that we can solve an logarithmic equation is get one logarithm of the same base on each side of the equation, and then use the one-to-one property. So we would get something that looks like this. So these are really the two main ways that we're going to do these problems. Get one logarithm by itself, and then rewrite in exponential form, or get one logarithm on each side and use the one-to-one property. But while we're doing this, we should not forget our other rules for logarithms, because sometimes we have to use those to work with our equations before we can do these things. So sometimes we have to do some combining of things or expanding to get our equation to work the way we want it to. And another thing that will happen sometimes when we do these equations, when we solve these equations, is you'll get two solutions. If you get two solutions, always check. Because sometimes you might get one that does not work. You'll get a solution, what we call an extraneous solution. You'll get a solution that's not actually a solution. All right, so questions on our guidelines. Okay, so what I want to do is go through a couple of examples, and then we'll talk about a couple of applications that have to do with continuous interest. All right. So we're going to solve. This first one is pretty easy. 2 log x equals 5. Well, this one should be easy. So what's the first thing we want to do? Get the log by itself on one side, so we divide by 2. So log x equals 5 halves, and then we rewrite in exponential form. So if we write this in exponential form, what's our base? 10. So 10 to the, rewriting in exponential form, 5 halves equals x. There's our answer. And if we plug this into our calculator, this is approximately 316.228. Now the other way we could think about this, just relating it back to how we worked with exponential equations. When we had an exponential equation, we took the logarithm of both sides. We can think about this, what we did here, as raising 10 to the power of both sides. What we call exponentiating both sides. So I could write this as 10 log x equals 10 to the 5 halves. So I raise 10 to the power of both sides, kind of the opposite of taking the logarithm. Well, 10 to the log base 10 of x is just x equals 10 to the 5 halves. We'll get to the same place. So rewriting in exponential form is the same as what we call exponentiating both sides. For this, because our base is 10, we raise 10 to the power of each side. Get to the same place. No, it would just say solve. It just, some people it helps them think about it this way, some people it helps them think about it that way. Just different methods. All right, questions on that one? All right, how about natural log of square root of x plus 2 equals natural log x. We had one. We could do some things here, but what does this tell us right away? We have a logarithm, same base on each side. So we're using the one-to-one property. Natural log of x equals the natural log of y, only if x equals y. So square root of x plus 2 equals x, using the one-to-one property. Now, how do we solve this one? How do we solve for x? Square both sides. So x plus 2 equals x squared. Now what do? We got x on the other, so we have a quadratic function, right? So we want to get everything on one side and get it equal to 0. So x squared minus x minus 2 equals 0. And now what do we do? Factor. Perfect. And we hope that this is friendly, so we get an x and an x, and we have to have a 2 and a 1. And it has to be a negative, a plus. So this says x equals negative 1, or x equals 2. We get two answers, so we should check. Do both of these work in our original equation? Two works. Because if I plug in 2 here, this I get the square root of 2 plus 2, square root of 4 is 2. So I get natural log of 2 equals the natural log of 2. If I plug in negative 1, I have the natural log of square root of 1 equals the natural log of negative 1. Is that okay? Natural log of 1 equals the natural log of negative 1. Is that true? What else is a problem there? If I plug in negative 1 here, what's our domain? What's the domain of our logarithmic function? X greater than 0. This is out of the domain. So that can't be a solution, so I throw that one out. We can't take the natural log. If I plug it back in here, I can't take the natural log of negative 1. Remember, our graph looks like this. We never plug in negative numbers into our logarithmic function. So this one out of domain, so our answer would be x equals 2. And we already checked that that works out okay. All right, we good there? Yes. It's possible that the equation is actually not an equation. So yeah, when it's always good to double check to make sure it works. Usually you're going to get something where one of the two works. All right, let's look at this one. A little trickier on this one. The log of x minus log of x minus 3 equals 1. Now this one doesn't quite work out like the second example, because if I add the log of x minus 3, I get log x equals log of 1 plus log x minus 3, and I don't have just two logarithm on each side. So what can I do? Remember, my third hint was to remember our rules for logarithms. Yeah, Sam? Turn it into division. Very good. So this is going to be x over x minus 3 equals 1. Now I have a logarithm by itself on one side, so I can rewrite this in exponential form. So to rewrite this in exponential form, I get 10, my base is 10, to the first power equals x over x minus 3. And we can solve this. This one's not too difficult. Multiply by x minus 3, so x minus 3 times 10 equals x. So I get 10x minus 30 equals x. So 9x equals 30, and x equals 30 ninths, which is 10 thirds.
How did you go from the
here to here. I rewrote this in exponential form. So this is log base 10, so then I just rewrote it in exponential form. So 10 to the 1 equals x. And you could also think about the raising, since our base is 10, raising 10 to the power of both sides. So 10 to the log x over x minus 3. It's the other way we can think about it, equals 10 to the 1. And the 10 to the power and the logarithm are inverses, so they undo each other. And you get to the same place. So you can think about it either way. All right, questions? Questions on that example? So this one, don't forget, this one was to help us remember to think about the other rules of logarithms. If you get to a place where you're not sure what to do, you can use your rules of logarithms to solve this. All right, want to look at a couple of application problems. So let's say we have, we want to double an investment at 8% interest with continuous compounding. So we want to double our investment. Well, first let's remember what our continuous interest formula was. Our amount equals, do you remember what that was? What was it? PERT. That was our P e to the RT. Someone was telling me they took, this weekend they took an ACT test and there was a continuous interest problem on it.
Yeah.
You were there?
Yeah.
This was on there? All right, so it doesn't give us an amount. It doesn't give us our principal. So if we start with some principal P, if we double our investment, what do we end up with? If we start with some amount P and we double it, what do we end up with? 2P. And with 2P. So this is our amount that we want to end up with. So I say 2P equals P, whatever it is, e to the 0.08 for our rate times T. Well, here's the really nice thing about this. I divide both sides by P. Those go away, and I get 2 equals e to the 0.08 T. Doesn't matter what P is. My equation turns into this. Now how do we solve this? We have an exponential function by itself on one side. Take the natural log of both sides. So I get natural log of 2 equals, when I take the natural log of that side, I get 0.08 T. So T equals natural log of 2 over 0.08. And that's approximately 8.66 years. And the nice thing here is that time doesn't matter what principal we start with. That is called the doubling time for continuous interest at 8%. Doesn't matter how much we start with. We can start with $1, we can start with $1 million. It would take us 8.66 years to double it at 8% interest compounded continuously. And in general, this is how you calculate the doubling time for this kind of thing. Natural log of 2 over our interest rate. That's our doubling time. And tomorrow we'll talk about radioactive decay, kind of the opposite problem. We'll talk about half-life. Half-life is the time it takes to reduce something by half. Same kind of idea. They're kind of inverse problems of each other. All right, questions on what we did there? Okay, let's look at one more. Let's say we have $50,000 to invest. We need $350,000 in 30 years. So in 30 years we need this $350,000, I don't know, to pay off our house or something. So the question is, what interest rate do we need if our interest is compounded continuously? So how would we set this one up? What is our $50,000 in our formula? We have P A equals P E to the RT. So what's the $50,000? What is it? That's our principal. This is P. What is the $350,000? That's A. That's the amount that we want to get. And the 30 years? T. So we just plug everything in. So we get 350,000 equals 50,000 e to the 30R. And we know how to solve this one, right? We want to get our exponential function by itself on one side. So we divide both sides by 50,000. So I get e to the 30R equals, in this problem it turns out to be 7. Then we take the natural log of both sides. So 30R equals the natural log of 7. And R equals natural log of 7 over 30, which is about 6.5%. So if we wanted this much money in 30 years, we need to invest it at 6.5%. So these turn out to be exponential equations, but we'll use logarithms to solve them. Questions? Okay. Homework. All right, there you go.